everyone, my name is Noah and I'm from the University of Wisconsin-Stevens Point CREST team, and today we're going to be talking about HIV protease. So HIV is a novel human virus that affects T cells and causes or can lead to AIDS, which is acquired immunodeficiency syndrome. Today we're looking at a view of the active site of the box of HIV protease. HIV protease is an important protein within the HIV life cycle that helps process the GAG and GAG-POL proteins into ensuring that the virus is able to replicate and later infect other cells. So because HIV protease is a homodimer composed of 99 amino acids, we can see here that our model has both of the halves of the dimer represented. So one half is represented in pink and the other half is represented in yellow. If we open up our active site box, we can lift this part off, and we can see inside that using the space fill orientation, we have shown that there's 3 or 4 key residues within the active site box that are the most easily mutatable. One of the problems with HIV protease and its fight with humans is that it can easily mutate these residues. So researchers have been developing different drugs that have been able to resist these mutation changes and still be effective even in the face of different mutations. Along with our active site box, we have also modeled several different drugs. One of the drugs we have modeled is called darunavir. This drug is one of the most widely available FDA drugs to fight HIV that is currently on the market. One of the issues with this drug is that when HIV protease mutates, the amino acids that mutate are commonly mutated into smaller amino acids, meaning that our drug, darunavir, does not fit as well. So if we open up our active site box here, we can see that darunavir fits in pretty nicely, just like this. It can go in either direction, it doesn't matter, because this is a dimer. And if we plop that back on there like this, boom, fits right in. So the major work with this project is trying to look at different types of drugs that slightly modify darunavir to have either bigger side chains in certain areas to fill the void missing from those common mutations, or to have different heteroatom groups that make more specific interactions with the protease itself. So on screen right now we have the FDA-approved drug darunavir. What the Schiffer group did is they took different analogs of darunavir. So we have UMass1 and we also have UMass6. What's different about these two drugs compared to darunavir is that these drugs have slightly bigger side chain groups than darunavir that were hoped to fill the gaps that were left when the protease mutated. Unfortunately, what they found after testing was that these drugs did not, in fact, work as well or better than darunavir as expected. So the Ki values for both UMass1 and UMass6 were measured for 2 different mutations, one for residue 84, the other for residue 50. These were both mutations that took isoleucine down to valine, which is making the protein have a smaller residue at that specific spot. And if the drug were to have a larger group, you would think that it would bind better. But unfortunately, as you can see from the graph, this is actually not the case. We also printed another drug by the Weber group called GRL142. This drug is also an analog of darunavir, and it has, like UMass1 and UMass6, larger groups and also some different heteroatoms in its side chains. The group tested this drug with different proteases that had multiple mutations, and it actually worked very well with these different mutations. The antiviral activity was quite low compared to DRV, and this is a very exciting drug moving forward in development of inhibitors for HIV protease. Moving forward, multiple groups are looking at different drug analogs of DRV, such as the ones that we have modeled here, with hopes of finding some that have even higher fidelity to highly mutated versions of HIV protease. There is hope that someday there will be a drug available to patients with HIV that is a successful inhibitor of many different versions of the mutated protease, with hopes that early onset of AIDS can eventually be prevented in all human populations.